One of the very unfamiliar concepts to many chemistry students is the idea of significant figures. Significant figures are simply the digits of a measurement that are known for certain, plus one digit that is always estimated. The final digit recorded in a measurement should always be an estimated value. The purpose of this is to communicate the uncertainty in the measurement that was conducted. Measurements with less uncertainty tend to be more reliable. Therefore, when one is recording a measurement, it's important to write down the information that includes the correct number of digits. These digits recorded would be called the significant figures. When looking at ruler A to measure the nail length, we can see there is much uncertainty in the measurement as there is only one mark on the whole ruler. All we can truly be certain of with this measurement is that the value is somewhere less than 10. Perhaps we estimate the value is 8. When looking at the second ruler, we can see the uncertainty is reduced because of additional markings on the device. Now we can be certain that the uncertainty is somewhere between 8 and 9, or the actual measurement is between 8 and 9. Therefore, we estimate a value in the tenths place, perhaps 8.5, maybe 8.6. The actual estimated value is not terribly critical, but it communicates to the user that there is better certainty in this measurement than there would be if ruler A were used. When looking at ruler C, we see we have improved certainty again as a result of additional markings. Now it appears that the nail length is somewhere very close to the 8.6 or 8 6/10 marking. Therefore, we would communicate by estimating a hundredths place beyond the tenths place. Perhaps it's exactly on the 8.6 mark, therefore we will add a 0. This communicates better certainty from the improved number of markings on device C. You can see the certainty of a measurement improves as the device markings are more precise. The correct strategy is to estimate a digit that is one decimal place position beyond the position that is certain. In the case of ruler B, the place position that is certain is only in the ones place, 5, 6, 7. Therefore, we estimate one decimal place position beyond the ones place, or we estimate at the tenths. When looking at ruler C, we can see that the small lines on the markings represent tenths. Since this is marked clearly by every 1/10, we must estimate one decimal position to the right of tenths, or hundredths in this case. Again, the point with significant figures is they communicate how uncertain or how certain measurements truly are, and it's always based on the type of equipment that was used to make a measurement. When we have improved equipment, we often have improved certainty in measurement. When looking at ruler A, we can see ruler A only gave us one digit that we would call a significant figure. Ruler B, however, gave us 2 digits that would be considered significant figures, and ruler C gave us 3 digits that we would call significant figures. The more significant figures we have in a measurement, the more certain we are about the exact measurement that we are conducting. Let's look at a few other devices where we record the correct number of digits. Here we are looking at cylinders that are marked by every 1/10 of a milliliter. Therefore, the certainty is in the tenths place, which means the estimated value should be one digit beyond that in the hundredths place. This is why the users have recorded 3.10 for a cylinder on the left, and then for the cylinder on the right, they have recorded 4.25. Each of these measurements include 3 significant figures. When looking at this cylinder, we can see the markings are clearly marked by every 1 milliliter. Since it is marked by every 1 milliliter, we want to estimate one digit to the right, one decimal place position to the right which would be in the tenths position. When looking at the value or at the level of the meniscus from eye level, we are somewhere between 44 and 45 milliliters. Therefore, we estimate a value between 44 and 45 by including a tenths place as the estimated value. This is the correct technique for this particular strategy in chemistry. Because the markings of the device are limited to the ones position, the estimate must be provided in the tenths position. This results in a measurement with 3 significant figures: 2 digits that are known for certain, 1 digit that is estimated, the final digit. Applying the same strategy relates to every device that is not a digital device. Sometimes these are referred to as analog devices. On this device below, we have a balance. We can see that there is a slider that indicates a hundreds position, a tens position, and a 1 and tenths position on the same slider. Recording this measurement correctly requires us to write down the correct number of digits. Therefore, we will record 500, which is certain, 40, which is also certain, 6, which is certain, and now we count the tenths. It looks like it appears to be 2 tenths. And now we are uncertain because there are no clear markings beyond the tenths on this particular device. This lets us know we should provide an estimated value in the hundredths. It appears it may be slightly past the 2 tenths mark, so we will add a 1. Perhaps you add a 2. The difference would really be the fact that you are just communicating the idea that you have estimated the correct digit. It does not make 546.22 grams any different than 546.21. It is just clearly communicating that we have estimated in the hundredths position as required. Because this device is clearly marked by the tenths, we must indicate an estimate in the hundredths decimal position. This particular measurement is made up of 5 significant figures. It's important to restate that the last digit is always an estimated value, and that is standard practice. This communicates where the uncertainty lies in every measurement recorded.